Okay, then, if we look on the trigonometric functions, for example, the sine x, if we draw the curve, and then we are doing the estimating the derivative through the graph. When we look at the graph, okay, the first thing that we can do is we can take sum of the slope, okay, especially the slope that is in the horizontal. So we take the horizontal slope, or we call the horizontal tangent, and then we are projecting to a new curve, and this slope should be equal to 0, right? The horizontal one. And then we can also have other slope as well. And then when we project it to new curve, it seems that we can predict that the derivative is going to be cosine x, okay? And that is true, but we need to have another proof. And the proof that we are able to write in steps is proof from the limit itself. Okay? So the limit, to prove the derivative, we always use this limit. Okay? Limit h approach 0, f x plus h minus f of x over h. Okay? So we are always using this terms limit to prove our definition of derivative. Okay, we deal with this. Okay, we are going to have the functions is sine, and then we exchange all the functions with sine. We get these expressions, and this expression is precisely this terms here. We can use this formula to make these expressions become sine alpha plus beta. Or in our case, we can take this and make it into our expressions here. Okay. And then we can have these expressions. Okay. We can have sine x cos h minus 1 over h plus cos x sine h over h. And if we look at the last expressions, we have some limit that is still unknown, and that is our goal today. Okay. We need to find what is this limit, still limit here, to prove that what the graph conclude is the same as what we are going to achieve. Okay. So first, we can take this. So we are going to prove that limit as, let's say, theta, to make it easy for trigonometric. First is this. Okay. Now to prove this, let me draw the circle. And then take the sector, some part of the circle, and let's name this A, O, B. Okay. And then imagine the circle is having it's not really good. Okay, it should be perfect polygons. Okay, it should be perfect polygons. But let me just take this another terms E. And then we take another description, that is, take this into a right triangle, and this is C. And take another line here. And then take another line that is here. Now this is another right triangle, and this will be D. So A, B, C, D, E. Okay. Okay. So first, maybe I'm making. Let's make the triangle looks bigger. Okay. Let's making bigger. Let's take all the terms O, A, B, and then take another extended this line and extended the other line. So this will be E, this will be D. I think we need to make it a little bit higher. This is C. Okay. If the radius of the circle is equal 1, R equal 1. Okay. If the radius is equal 1, and we have an angle between the two lines between the two radius, okay, which is theta. Okay. If we take a look on the circle itself, okay, if we want to calculate the arc, so arc AB, okay, if this is theta, this arc here, the red line here, the red curve, the arc will be theta over 2 pi multiplied by 2 pi r. Do you get it? How can I write this? This is because the circle has 2 pi, right? And 2 pi r is basically the total circumference, right? Which means that the length of the circle is 2 pi r. So if we cut the circle and we extend the curve, so if we cut one side here and we take it into the straight line, those length will be 2 pi r, right? So if we have just taken slightly curve here, that means the ratio between the theta here compared with the whole circle multiplied by the total length, right? Okay. So the arc or the curve will be, so arc AB will be theta r, right? And because our r, we assume from the given information, our r is just equal 1. So we can say that arc AB is just equal theta, okay? Just to make our calculations easier. So arc AB will be theta because the r is equal 1, right? Okay, now if we look the circle and the triangle now, if we take the distance between BC, take a look the triangle OBC. BC will be OB sine theta, right? Okay, let me write here. Sine theta means BC divided by OB. So BC is OB sine theta, right? And OB is our radius, which is equal 1. So I can write BC is just sine theta, okay? BC is just sine theta. So BC is sine theta. Okay. Okay, now if we look the length between BC, we compare BC, BA, and the arc. BC is of course less than BA, right? The length. If you draw the length, if this is a right triangle here, and you have another hypotenuse here, of course the hypotenuse will be longer, right? Okay. And then this hypotenuse is less than the arc, right? Because the arc has some curve in here. It's not the same length, right? So I can write the distance that is BC is less than AB is less than arc AB. Arc AB is theta. BC is sine theta. So sine theta is less than theta. Or we can write sine theta over theta is less than 1. At least from what we have done, okay? At least. Okay. Now, another point of view is we can see that we have the arc AB, okay, and compare with the distance AE and EB. Okay. Let's compare those distance. Okay. Of course, if we look on the arc AB, it will be less than the distance from AE plus EB, right? Let me draw another one here, okay, to make it clear. So this is AB, okay, and you have another distance here and here. Well, it's not actually, it looks like the same, but let's just say that this is A, B, E. Okay. So the arc will be less from this distance plus this. Okay. And of course, if we look on the AEB, right? So arc AB is less than AE plus EB, and arc AB also less than AE and EB. Okay. So if you draw with good proportions, with the good proportion in the polygons, you will see that it will perfectly align. So we can write that the arc AB is also less than AE plus EB. So this distance here, or we call the AD, AE plus ED, this distance, and if you have theta here, okay, if we have theta, then tangent theta is equal AD over OA. And because OA is radius, which is equal 1, then we can say that AD is equal to tangent theta. So here, arc AB is less than AD, which is arc AB, or we can write theta less than tangent theta. Or we can write theta less than sine theta over cos theta. And so, from these two inequality, we can take a new inequality which includes cos theta is less sine theta over theta less 1. And then we take the limit. As theta going to 0 of 1, this is just 1, and limit, or maybe I will write on the right side here, and limit as theta going to be 0 for cos theta, this is also equal 1. So by squeeze theorem, remember that we can imagine this as functions. So by squeeze theorem, limit if we take the theta is just from 0 to pi over 2 to make it easy to observe only one quadrant, then this is also equal 1. But we can take the general rule because sine theta is the sine theta over theta, this is even function. Meaning that it's symmetrical. So the right limit and left limit should be the same. So the general terms we can write the total limit will be equal 1. So this is our conclusions from this proving. Okay. This proving is also important because sometimes if we have limit, and remember that if you know or maybe remember about L'Hopital rule, right? So if we have 0 over 0, right? You can derive, and you derive cos theta, and it's 1. Cos 0 is 1. Oh, it's true. But actually that is wrong steps or wrong process. Do you know why? Okay. So here's the thing. So what we are doing here, we are going to have this limit and proving that this is equal 1, right? Why we are doing this? We are doing this because we need this proven, this to be proven, so that we can exchange this from 1, right? And this itself is how we can prove that the derivative of sine is cosine. So when we are dealing with the 0 over 0 situation, in some case we can do some L'Hopital rule, in L'Hopital rule we are going to use derivative. And where derivative comes from this. So you are breaking the rule. So that's why it's not allowed. Okay? So this pretty much is basically a definition. So when you have this kind of questions, you can just write, okay, this is just equal 1, because it's basically a definition that we have already proven at the other slides, and this is our proof. Okay, at least from geometrical perspective, and there are other approaches with different geometry, and we will have the same result. But at the end of the day, this will be the definition. So whenever you find a limit in terms of some trigonometrical functions that is maybe looks complicated, but you think that you can simplify, and you can find this this form, so you can maybe factorize this form from the complicated limit. You can always do that, and you can take the conclusion. Okay, I can take this to be equal 1. Okay. But we are not finished yet because we still have this, the other one, the cosine here, the left. Okay. So how we are going to prove this? Okay. If we take this, let me take the whole thing here, become here. Okay. So first, let me write so we are going to prove this. Or maybe this probably erase this first. Okay. So we are going to find how we can simplify this equation. Okay. Now remember, in limit, okay, this is just another review on limit. In limit, if you look on the equations, the first thing you can do, check the limit. Okay. The first thing is check. Okay. So first is always check the limit. Okay, if you get some value, maybe 2, 3, 1, 0, then that is your limit. You don't need to evaluate another more steps. Okay? But when you take the limit and you check the number put inside here, like here you have 0 over 0. Okay? We call that is the indeterminate forms. So 0 over 0, we cannot sure whether it exists or not exists. There are several ways to justify. So second, if 0 over 0, then what you can do first is rationalize. Second, if you have factorization, you can factorize. And maybe if it's trigonometric, you can use special trigonometric or trigonometric formula. If you can simplify and change the form. Okay. It seems that because we are having cos theta minus 1. Right? We have minus. So what's happened with this if we multiply cos theta plus 1 over cos theta plus 1? So let's do that. Okay. Now this becomes cos squared theta minus 1 over cos theta plus 1. Okay, what we can do first is, if we have the squared like cos squared, we can use the sine squared plus cos squared equal 1, this identity, so that this will be 1 minus sine squared x, right? And then you can simplify and cancel 1, and it will be just minus sine squared x that left. Oh, I forgot the theta, sorry. So theta, I forgot to multiply this. Okay, now what we I'm going to do, we can then split up the trigonometric. So maybe minus sine, why is this x? This is theta. Sine theta over theta, and multiply with limit. I can separate the limit sine theta over cos theta plus 1. This will be minus 1 multiply with, we check the limit, it's 0, it's 2, so 0 over 2 is just 0, so it's equal to 0. So now we have also proven that limit, so in conclusions, limit is 0. Okay, so whenever you find any trigonometric equations that you can maybe you can factor out these two terms, this cos theta minus 1 over theta and sin theta over theta, you can directly write sin theta over theta equal 1, and cos theta minus 1 over theta will be 0. Okay. And you can make also a conclusion from the previous one. Let me just write the conclusion here. That this limit will equal to, because this is 0, so this will be 0, plus this one is 1 and cos x. So this will be limit cos x, or this will be equal just cos x. So this is the first derivative. So we can take the derivative of sine x. This will be equal to cosine x. Okay. Okay. Do you want to still write the notes from here or from here? Okay. Okay, I think I can write some summary for the trigonometric. At least we have this. And from the same process, we can also get this cos x. If you want to try, you can try by yourself. This will be equal negative sine x. And then if we have tangent, if you don't know how to derive tangent, we can derive by taking sine over cos like this, and we can do some quotient rule. So this will be cos squared x. Okay, imagine this will be f g. So quotient rule will be f prime g minus g prime f divided by g squared. Okay, so that's why we get cos squared x on the bottom, and then cos x and then minus negative sine x, and this will be cos squared x plus sine squared x over cos squared x. This will be 1 over cos squared x or secant squared x. So derivative of tangent will be secant squared. The same way, if we derive secant x, we can exchange secant with 1 over cos and do with the quotient rule if you want. This will result secant x tangent x. I think the other one, like cotangent and cosecant, is not really important. Well, if you forget, you can just do the quotient rule. Okay. If you look on how the sine and cosine correlate each other, if you derive sine, it will become cos. If you derive cos, it will be negative sine. If you derive one more, it will become negative cos. It will be exchanging sine, cosine, right? Always, all the time. If you derive like many times, you derive. For example, if we need to find, for example, find 27 derivative of cosine. Well, it seems that you can do that like manually, like 1, 2, 327. But if maybe we increase maybe 100, 200, 300 times, it will be really tedious, right? You will be maybe you will have some in the middle. Maybe you have mistake or the signs plus minus, right? But how we can deal with this kind of questions is we can take the derivative. For example, if the function is cos x and we take several times, okay, maybe until 4 or 5, we take the first derivative. This will be negative sine x. The second will be negative cos x, and then the third time it will be sine x, and the fourth time, usually we write the derivative first, second, third, but after third we are just writing the number. So if you see like this 5 or 4, 5, 6, it means that it's derivative 4th time or 5th time. Okay. So we derive again, it will become cos. So after 4th time, we are going back to the original equations, right? It's going back here. So of course, if we are looking here, 4, so if we have 5, 6, 7, and so on, right? So we can have some pattern from here. So from this pattern, every cycle, or let me write in a cycle of 4, there is original functions. So fn of x equal cos x whenever n is multiple of 4. So we can write f 24, because 24 is 6 by 4, right? 6 by 4. And 24 is closer to 27, right? Closer to 27. So this will be cos x. So 27 will be 24, 25, 26, 27. So 24, 25, 26, 27. And we get the 27 times its sign. And later, if you check some exercise, you will see maybe it's not always this simple. Maybe it will have some complication, but still, if you check the pattern, it will have some pattern. Okay? But you need to maybe careful with the signs, careful with the positive, negative. Okay. Okay, another example, okay, regarding the limit that we talked before, the limit of sine x over x or sine theta over theta, we can apply those limits into this example. Okay, let me just finish this and then we can have a short break. So this example, it seems that we need to add another terms. Okay, so first we want to have this kind of equations, right? Which is equal 1. But we have difference on this. This is 4x and 7x, right? What we are going to do is we want to make the bottom one having the same as this 7, right? So what we can do is let me just write this sine 7x. First, we can write, we want this, right? We want this. How we can make this equal? So we need to multiply with something here. Okay. So what we can multiply is 7 over 4. If we multiply, we are going back to our original equation, right? 7, 7 is 4x, 4x, right? So let's do that. This is, I think, easy to look at. Then this will be the limit as x equals 0. And we can treat the 7x as a theta or x, just x, right? It's the same terms as in our case here. So we can finally see that this will be 7/4 limit and this will be equal 1 and this will be 7/4. So you know how to make a shortcut. So whenever you have something like this, you can basically directly say, okay, 7/4. But this is how you're going to explore. Okay, we can have a little bit short break, and then we can continue for maybe reviewing limits, or maybe continue a little bit derivative and then reviewing limits, and some questions maybe if we have. Okay, so yeah, we take a short break. Okay. Okay, let me start with the chain rule. This is chapter 3.4 if you look on the textbook. Let me write the terms first, okay? What the chain rule means. Okay. So if function g differentiable and function f is differentiable at g, then composite function, let me write it with the capital F and an F of g, and it's also defined, or maybe let me write it in here, f of x is f, and then inside those function is g, and f of x is differentiable at x. Okay, so we set up our assumptions to be set for our calculations for derivative. So g is differentiable at x, and small f here also differentiable at g, and the capital F, the other functions, is also differentiable at x. So based on these assumptions, so we can take the derivative, f prime x becomes f prime g of x inside, and then multiply with g prime x. So what's happened here is actually, if we look on the terms, so the derivative is basically, if we have this composite functions, first we can think the composite, the small f, as outside functions. And g of x, we can think g of x as inside functions. So what really happened here is when we take the derivative, we take the derivative of the outside functions, just a small f. We take the derivative of the inside functions, which is g prime of x. But if you look on our case, we only have one function inside the functions, right? But it can be more than one functions. Maybe this x is another function, and then inside another functions it can be. But the principle is still the same. The principle is still the same. So we are having outside functions we derive, and we are having inside functions derive the derivative. Okay. If this is another functions, then we need to also derive the function and multiply with other functions, and we have many more. We have more and more in composite. Okay. And we can also write in terms of the Leibniz notations. So if you use the Leibniz notations to write, and I think I prefer the Leibniz notations better, because if we have, for example, y is function of u, and u is functions g of x, okay, both differentiable, functions, then dy dx is equal dy du and du dx. Basically, if we have defined y is functions of another variable, and we have some variable, this can be any variables, is function of x, we can take the dy over dx and we can chain them up. That's why it's called chain rule. So it's like it's chained together. So when you have like more than one function, maybe 2 or 3, and they make a composite, you can have like dy over maybe du over dv, dv over dw, dw over dx. So it has many chain. Okay. Like for example, if we have more than one, we can take this in the case that maybe this will be u, and then dv, and then dw, and then w and dx. So it has many chain. So it does makes the chain rule makes more sense. Okay? The chain, okay? The chain of the Leibniz notations. Okay, of course, in the chain rule, this is the theorem, okay, but of course the theorem needs to be proven, and the way we are going to prove this is through the limit definition of derivative. So let me write in the new slides here, and let me take maybe 10 minutes to prove. Okay. So if y equal f, I think I write maybe f of x, okay. And then as x is change from a to a plus delta x, we can set up the difference on delta y. So I hope you can imagine this like in terms of a graph. Okay, so if you take the functions and we take the change in a, and we have another one here that is plus the x. This means that this is having change in y, right? So we can write as delta y. So as limit approach delta x approaching 0, so if we take this and divide by delta x, this will be delta limit of delta y divided by delta x, which is f prime of a. Okay, I think we already know this, right? This is just for the intro. If there is number epsilon, that is the difference in delta y over delta x and f prime a, okay, then the limit as delta x getting 0 of the epsilon, we can write this in terms of delta y over delta x minus f prime a. Of course, if we look closely, this means that because limit of dy over dx, this will be equaling f prime a, this saying that this is getting to be 0, right? That is if we are going to include the limit. But the reality, we will still have the epsilon that is the difference between these two. Okay, let me take this as our first equations. Okay. So we are going to use this epsilon to prove that our composite or our derivative in composite is true. Okay. Our delta y then we can write in terms of f prime a delta x plus epsilon delta x. And as delta x going to be 0, epsilon is also going to be 0. And suppose we have another function that is in variable u. Let's say it's g, okay, and then we have our y. Okay, this is in terms of u. So that's having these two functions. U is differentiable at A, okay, and y is differentiable at B, but B is equal to function g of A. And if we have delta x, delta y, delta u, this is all small distance or small increment of x, y, and u. And let me write the second one here. Then we can also write delta u using the definition of u is a function of g, so g prime a delta x plus, let me write the epsilon, but let me add 1 to make a difference with the previous one. And then we can write this and factorize the delta x, okay, and then as delta x getting 0, the epsilon 1 also getting 0. And then the last one is delta y is f prime b delta x plus epsilon 2 delta x. Oh, and here is u for, sorry, it's become u. So as delta u getting 0, epsilon 2 also getting 0. And now we can combine these two. Okay. We can combine. So delta y is equal f prime b plus epsilon 2. This should be delta u, right? Delta u, but delta u is also equal with this. So let's write the whole thing here. G prime of a plus epsilon 1 and then delta x. And then we can write this in terms of delta y over delta x. And then by definitions, we can write dy over dx is limit as delta x going to be 0, delta y over delta x, or this is going to be f prime b plus epsilon 2 g prime a plus epsilon 1. This is as delta x going to be 0, epsilon 1 going to be 0, epsilon 2 also going to be 0, which means that dy over dx is proven to be f prime b g prime a, or f prime g of a g prime a. Okay, this is just to note that we can take the the delta y over the delta x. So the difference between delta and the d is delta. It means that we are going to approximate. We are going to use the limit to make our definitions clear to be the derivative. Okay, and then from here, what actually we are doing is we are including our epsilon as the real small gap or small increments, okay, between the delta and the actual derivative. Okay? Because we are in limit situation in which we have a small distance that we are going to close the gap, right? We are going to close the gap. And how much the gap is described by this epsilon. Okay? And then we can take this this definition of epsilon, okay, this definition of epsilon, and we can retract a line equation of the delta y. Okay? So delta y becomes epsilon delta x plus f prime a delta x, which is on the right side here. So we can write this, and we can write other functions too if we have the other function as the u, y, and then g. So we can write all this, and this is what we have. So we have u, we have y, and then we can combine these two all together, and then we can write here, and we have two epsilons now, epsilons for the delta u and epsilon for delta y. Why we need to include this epsilon? So that we can prove at the end of the day what we are assume at the very beginning is actually true. Okay. So that we have now the dy over dx is in the composite functions, it becomes this expressions as we assume at the very beginning on the chain rule. Okay, up until here, is there any questions? Is there any questions? Well, you don't need to understand now, but later you will be able to understand when maybe you are actually having another course that that describe more about the discrete, the continuity in another, maybe more like maybe linear algebra or other course as well. Maybe you will understand at some point what this truly means, what the epsilon truly means, from maybe from statistics, from data you have. Maybe you will learn more. Okay. Okay, let me just take some time to review and have some practice. Okay? So far we have discussed, so the chapter 1, we discussed functions. And we discussed, from this part, we discussed what function is, and then the range, domain, right? And there are several typical functions that you encounter typical functions. Like the polynomial, rational functions, trigonometric, exponent, also log. Okay. Well, I'm not really reviewing all before, but I hope you still at least know the difference. Okay. And from functions also we are discussing, we can transform the functions. Which means we can shift the functions, okay? Shift it to the right, to the left, going up, going down, and then stretch the functions, stretching up, stretching vertically, stretching horizontally, okay? Mirroring the functions, okay? Mirroring the functions, like this one is going to be minus or. Please check the difference, okay? Transformation of functions. Also, we have the inverse functions. The inverse, which going to have the requirement, which is one-to-one functions. And of course, we also know how to check. We can check through the horizontal test, right? Horizontal line test. If we want to check whether it's functional or not, we can check with the vertical line, right? This is also include the composite, the FOG terms. What else? Yeah, I think this is most of our discussions. The typical function also include whether the function is even or odd. Yeah. And of course, the basic, which is all the algebra, you need to be familiar with. Okay, so for algebra. If you're still having difficulty on algebra, please check by yourself. Okay. Please check, and you need to catch up if you're having difficulty on the algebra. Okay. And chapter 2, we are introduced by the tools limit, in which we are observing from the tangent and velocity problem, right? And then we have the limit law and precise definition of limit. From here we get the continuity, of course this should be having the definitions, and then we have also right hand limit or one-sided limit. Limits at infinity. And also introducing the derivative. by limit definition. And also derivatives as a functions. At least this is observing derivative through graph. Okay. At least we cover all of this. And for the quiz, maybe not all will be in the quiz, maybe several of them, but just to make sure that we know all the terms here and we prepared for all these terms. Okay. I think I can give you some idea on the case. I believe chapter 1 is okay, right? Is there anyone still having difficulty, maybe how to transform functions, how to get the inverse, or a composite? I think okay, right? Domain range, is it okay? Domain range is okay, right? Okay, let me just give you chapter 2 some exercise, again, maybe one or maybe two or three questions. So find the value. Let's try 2 questions first. Okay, I think I hope it's still okay, right? So first, check the limit, okay? Check the limit, and you see that it's 0, 0, okay? Okay, but we are not using any L'Hopital rule, okay, for today because there will be another chapter to be discussed. So first,
we can take these terms and we multiply and rationalizing. Okay, we're rationalizing. We can cancel, and then we can approach this with plug in, and it will be half, right? I think that's easy. And for this one, also same method. Okay. This we can have factorization. You may multiply with the another rationalization with this one because it's having a square root, or we can also factorize this x minus 4. Factorize becomes, we can also do this. Okay. Same result, same result. Oh, wait, wrong. Square root x, not square root of 2. Yeah, okay. So we can do that. This will be cancel, and then check the x equal 4. This will be 4 plus 4, so it will be 32. Okay. The same result. So any method, as long as algebraically true, then it will be true. Okay, let me go through maybe 1 or 2 questions. Okay. Sketch a graph of a function f that satisfies domain of f is all real numbers except 0, and limit as x going from the left of 0 is equal 1, and the right hand limit is 0. And then we have f prime x is positive for all x in domain of f, and the limit of x going to negative infinity of f prime x to be 0, and the limit as x approaching infinity of the derivative, this is equal 1. Okay, it's sort of guessing this the curve, but you need to guess correctly. Okay, so maybe the curve not to be like no need to be like really smooth, but at least from all this condition it should be fit in. Okay, it should be fit in with the conditions. And remember, to connect the functions to the derivative, remember the slope. Remember the slope, how the slope might be. So at least for the first statement, okay, you need to have 0, right? 0 as your consideration. Because from the 0, the left is going to be 1, right? The right interval is going to be 0. Which means the curve, how it looks like, is going to approach to 0 from the left, it's going to approach 1. But from right, it's going to be approaching 0. Okay. At least there is some connections. Okay. And you know, if you have the 0 itself, will be undefined, right? At 0. At x equals 0, the function is undefined. Okay. So you have something from the left that is going to equal 1, it's approaching 1, and from the right is going to approach 0. And the f prime is always positive in all domains. So which means the sketch that we are going to write or we are going to draw, they all need to be positive slope, which means it's all going to be increased. Okay? It's going to be increased. And the last statement, it's going to help us. The f prime itself, okay, when you have a limit, as it's going to go to the far left or going to infinity, it's going to be approaching 0, which means the slope of our function, the slope should be 0 when it's going to have infinity. So it's like the horizontal asymptote. Okay? This we have horizontal asymptote here. Here, when x is going to infinity, the slope is equal 1. Or if you can imagine, it's like y equal x. The gradient is 1, right? So it means that the gradient is 1. Okay? So what we are going to do is we can draw first. The statements say that when x equals 0, it will be undefined. So we can have maybe some 0 and maybe 1 is here. That will be a discontinuity. Or maybe we can write the domain stated from, we can write this, okay, to make it clear. And we need to make all the functions or all the curve should be increased. So maybe it's increase about this. And maybe increase on here. Okay. Why I draw like this? Because this is related to our slope. Okay? Our slope. Our slope should be 0 when we are going to have like the negative infinite. Okay? So negative infinite here. Okay. So we are going to have the slope is going to be 0. This is slope equals 0. And here is when we have slope is equal 1. At least this is the sketch that the questions want. Okay. Well, this is a little bit tricky for the f prime equals 0, because if you just think about the slope equals 0, then you might think that it will be just a straight line, right? But we know that it should be a positive function, right? So the slope should be positive. So there should be a slight increase. Okay? There should be a slight increase from the curve. Okay. And if you think maybe the line is just here, maybe it's not really that that fit in with the terms that slope should be positive. If we look here, we know that it's always increasing, right? It's always increasing. And we can ignore the discontinuity here because we are just include the domain. Okay? We just include the domain. Okay? Don't worry about the middle one here, because it's stated that the slope is positive for all x in domain. Okay? So we can ignore that is outside of domain. Okay? And we know that this is positive, this is positive. Okay? It's different if we are going to connect this and then going down and then increasing. We have some increasing here if we have some continuity here, right? But because here we exclude them, we don't include the point here, we remove them, then this is all in the statement. Okay? It's fit in with the statement. Okay, maybe I will give you maybe a picture. Let me check the picture. Okay. At which x, okay, so this is at which x function is not differentiable. So differentiable means that first the function is to be continued first. Okay? Of course. Okay? So if we have discontinuity, it cannot be differentiable. So at x -4, I can write this is discontinued. And then another aspect is if you have this tip, this sharp point here, as we mentioned before, we can trace this by a limit to prove that it has different slope, right? It's going up and it's going down, and we don't really sure what happened in this sharp point. Okay. So here, so x equal -1 is having the function has a corner, and x equal 2. This is also discontinued. So this is discontinued here, and x equal 5 because of vertical tangent. Okay. Here, vertical tangent here. Okay. So I will probably include some analytical observation on graph, so you can have some time to learn. And I think you still can get another preparation from your teaching assistant for this week, or at least chapter 1, chapter 2, or the quiz for Friday. Okay, I think that's it for today.